Hi, this is part 17 of a series of videos about multivariable calculus using the computer program called Mathematica. It's also the 17th part of a sub-series about calculations with parametric curves, and you could even say it's part 2 of a sub-sub-series about the relationship between parametric curves and polar coordinates. I will also introduce a new Mathematica command called PolarPlot near the end of the video. So here's the example. You should probably get a piece of paper out and try to draw what's going on. Here you've got a plane, and you should draw x and y axes on the plane, and draw a point P, whose distance to the origin in the plane is 5. We're going to label that with the letter R, and such that the ray, starting at the origin and going through P forever, OP, this ray makes an angle theta equals pi over 3 radians, which is 60 degrees, with the positive x-axis. Okay, pause the video and draw it. Once you're back, what we say is when that happens, when we've described P in this way, we say that P has polar coordinates given as an ordered pair and labeled with the letters R and theta. R comma theta equals 5 comma pi over 3. The first coordinate of these polar coordinates gives you the distance to the origin, and the second coordinate there, pi over 3, gives you the angle in radians in this case that this ray OP makes with the positive x-axis. Our main goal here is to try to figure out the regular rectangular coordinates of P. Alright, and in part A we're going to relate this to parametric curves by using curves to figure out what those rectangular coordinates are. Look at these parametric curves here. This one's C1 of theta. Theta is the parameter. By the way, I need to emphasize that these are actually given in regular rectangular coordinates as we've been doing to this point. This formula, 5 cos theta, gives you the x-coordinate as a function of theta, and the second thing, 5 sine theta, gives you the y-coordinate of the point as a function of theta. I hope you realize, based on what I've talked about before, that this is going to generate a circle, or an arc of a circle, as theta goes from 0 to pi over 3 radians, centered at the origin with a radius of 5. The second one, if you think about it, it really is a linear function of r. We've plugged in theta equals pi over 3. As when r is 0, this is going to be at the origin and is going to generate a line, a ray in fact, as r is positive and goes to infinity. This ray will go off to infinity. We will ultimately stop it at r equals 5, however, so we'll get a line segment. We're going to use these two things to visualize how to determine the rectangular coordinates of P and then actually find those coordinates. Secondly, part B, in general, we're also going to find, given the polar coordinates of an arbitrary point P in the plane, how do you find the rectangular coordinates of that point? I've got some Mathematica code plugged in here already. Don't know why that's smaller. Alright, got some Mathematica code down here. I'll briefly review the Mathematica code, but you don't have to understand this to appreciate the main point of the video. C1 of theta is right there, that's the formula. C2 of r right here. I'm entering the functions when I do this. I'm going to create an animation because I have a manipulate here. I've got two animation parameters, A and B. A starts barely bigger than 0 and goes up to pi over 3. B starts barely bigger than 0 and goes up to 5. I have one more 0 in here for B, that's not a big deal. A is the right end point of the interval that I plot C1 over. Theta goes from 0 to A. And B is the right end point of the interval that I plot C2 over. R goes from 0 to B. So as A and B change, this creates an animation because we get bigger and bigger pieces of each of these curves. I've added some other options. I made the axes thick with axes style thick. I've labeled the axes with axes labeled. I'd put the origin at 0, 0 because it's sometimes goofy and doesn't do that. I've added in some grid lines. This is something new I don't think I've shown you before. You'll see what the grid lines look like in a minute. They will be purple with grid line style. I made the plot range by putting a 6 here, go from -6 to +6 in both the x and y directions. I am combining two graphics with show. The first thing is this parametric plot, the second thing is this parametric plot. And again, all the rest of this stuff before the end of this show is there are different options to make it look nice. So let's see what it looks like, and then answer the questions. So here you see axes x and y, and you see a regular rectangular grid over these axes. As A increases, I get the arc of the circle, and as B increases, I get the ray. And based on how I picked the final values of A and B to be pi over 3 and 5, they are indeed meeting at the point P. The point here now is to see that it should look like the x-coordinate of P is about 2.5 and the y-coordinate of P is about maybe 4.3 or so. How can we find that? Well, I would encourage you to think about it on your own. You might want to draw a right triangle. The rectangular coordinates of P are what? Draw a right triangle or think about these parametric curves that we used. In fact, hopefully you realize that if you plug in theta is pi over 3 into C1 or r is 5 into C2, you will get the same answer, and they will be the rectangular coordinates of P. xy is 5 cosine pi over 3, which will be 5 halves because cosine of pi over 3 is going to be 1 half. And then 5 times sine of pi over 3, that'll be square root of 3 over 2 times 5, or if you prefer as a fraction, 5 root 3 over 2. The first thing, 5 halves, is exactly 2.5. The second thing, if we approximate it like this, is about 4.33013. Those are the rectangular coordinates of P. That is the answer. How about the rectangular coordinates of an arbitrary point, P, given in polar coordinates by r comma theta. So I've got an arbitrary r and theta representing the arbitrary polar coordinates of the arbitrary point P. Think about that as well. I hope you realize, based on, again, maybe how I made C1 and C2, that x-coordinate of P is going to be r cos theta, and the y-coordinate is going to be r sine theta. Okay, that's the exact expression for the rectangular coordinates of P. Okay, so that's the answer to the second part here, part B. And I would encourage you to try other examples. What I'd like to do to focus on trying to finish the video is I'd like to add some other options in here, and I'd also like to use PolarPlot like I mentioned at the beginning before I show you the answers to your exercise. I want to say that you can change the grid lines to being something different without automatic. I can, for example, put grid lines perhaps at -3 and 5 if I like in the x direction, and maybe -1 and 4 in the y direction. This would be the syntax that would create grid lines wherever I want. Kind of strange to do that, but there I did it. I made grid lines at x equals -3 and 5 and y equals -1 and 4. I liked the grid lines to be at every integer value between -6 and 6. I'm going to use the table command as a shortcut to doing that. I've shown you this before. What this bit of code does right here is it generates a list. I'll show it to you here. A list of numbers between -6 and 6. The integer values between -6 and 6. So if I type in table in the grid lines like this, that is going to generate this particular list, and is going to create grid lines at the x coordinates of -6 to 6 as x goes up by 1 each time. I can do the same for the y coordinates, and I get a finer grid to see this a little bit more precisely. I'd also like to use the command PolarPlot, like I mentioned. Let's do it down here, to add a polar grid to this. For the sake of time, I'm not going to explain the code for PolarPlot. In fact, I'm going to copy and paste the code that's down here to save some time. In the next video, I will take the time to explain this, but in this one I'm not. It is the use of PolarPlot. Don't worry about what the 20 means. Theta goes from 0 to 2 pi. This ultimately creates a polar plot, and I have to explain that in more detail in the next video. I do have a polar grid lines here that is going to make a polar grid like I showed you at the very end of the last video actually, and I'm going to make it orange. This will be our last thing to look at before the exercise. I need to actually put it in the show here as well. Polar grid is what I've named this polar plot. So I need to put that within the show. And now I have a polar grid on top of the rectangular grid, and we can once again see the relationship between everything. I would encourage you to think about this. Here's your exercise. That'll give you a chance to think about it. Pause the video, look this over, try to figure it all out. And then, well, I guess I don't have to do part B. I just copied and pasted there. We've already done part B. Use this exercise, and here's the answer that you should get. Those are the rectangular coordinates of P, and we can enter some other stuff to visualize what's going on here. I actually also put a point, a dot with list plot at the point we were at. There's a point whose rectangular coordinates, well, whose polar coordinates are r equals 3 and theta equals 3 pi over 4, and whose rectangular coordinates are given approximately by these things, and that's what I'll end the video with.